Okay, welcome everyone, and welcome also I got this video thing going, so I'm going to say welcome to all those watching online. And I hope this is working too, so if you're watching this online, I'm hoping that you can see the study guide that's up here. I know all my students, obviously in the classroom, can see it, but we're just going to bang out this thing very quick. It's kind of long, but we're going to try to get as much of it done as we can in about an hour, and actually an hour less, 7 minutes. And I'm going to go very fast, so this is just kind of like it's kind of a cram session, really, you know, because hopefully this is not the only thing you've done to study for the test, but if not, it'll at least help you hopefully to pass. So anyway, without any more ado, I'm going to get right into this, and we're going to go over these questions. So first one, it says, let me get this draw tool out, which might be kind of useful. Okay, so first one here is, what does it mean that science is empirical? All that means is that when we say that science is empirical, that word empirical means it's based on observation. Okay, so if I ask that on the test, you just want to say it's based off of observations. Okay, so those are things that you actually encounter with your five senses that we can detect about the physical universe. Okay, so that's all you need to say for that. It's pretty straightforward. You should kind of know the 5 steps here of the scientific method. And, you know, I just want to make this clear, beyond just, you don't want to just memorize like 5 words here, okay? You want to understand each of these. So the first step here is observation, right? So you start off with an observation that kind of makes you say, that's interesting. You know, I wonder why that happens, okay? Science is all about trying to explain causes, why things happen. X happens because of Y, okay? The next step here is you make a hypothesis. So regarding your observation, I wonder why that happened. I think it happens because of X, okay? The next one here is you make a prediction. Now, a prediction is different than a hypothesis. This is a question I often ask. Honestly, I can't remember if this is on your test, but I often ask it. Colton wants to know this because it's probably on the earth science, my earth science class, it's probably on there. But I often ask about what's the difference between a hypothesis and a prediction. Okay, the difference between a hypothesis and a prediction. Now, prediction it's obvious in a way, but a prediction is just a guess about what's going to happen based on your hypothesis. Okay, if this happens, if Y happens because of X, then I expect to see this, whatever that is, okay? So a hypothesis is totally different. A hypothetical statement is causal. It's saying this happens because of Y. X happens because of Y. A predictive statement is just saying, I expect to see this. I predict I'm going to see this if my hypothesis is true. So that's how you would tell the difference between those. Okay, now the next one is you actually test your hypothesis. Hi, welcome. You actually test your hypothesis. And for those of you who just came in, do any of you need a study guide? Because I printed out a limited number based on the number of people that said they wanted one. Okay, here you go. All right. So then you test your predictions with an experiment, and then after that you're going to do some kind of analysis. The last thing is you're going to do some kind of analysis that says, well, do my experimental results corroborate? Hello. Hi. Do they corroborate or do they deny or falsify my hypothesis? Okay, so then you go and you either accept or reject or modify your hypothesis. Do you need a study guide on that? That's okay. I have one. You need one? Okay. All right, you should also know the difference between quantitative and qualitative, right? So quantitative observations involve a measurement. Quantitative involves a measurement. You're measuring something and you're assigning a quantity. That's what gives you quantitative. Qualitatives, you're describing qualities. So there's not going to be any measurement involved. You're just kind of a description, okay, using adjectives and words instead of numbers, okay? Difference between a hypothesis and prediction, like I said, hypothesis is explaining, it's giving a causal statement. You're giving a cause. X happens because of Y, okay? A prediction is just simply saying, I think that whatever X outcome is going to occur. if my hypothesis is true. Predictions, by the way, should be, if they're properly formulated, they should be if-then statements. If my hypothesis is true, then we expect to see this. Okay. All right, so true or false, is it possible? I put this in almost all my tests because this is like the main point I want to get in people's minds. Is it possible for science to answer every single question? It's false, right? And it can't even answer that question. Right? Science can't answer that question. That's right up there, number 5. So you know that it's false. So anyway, describe at least 3 criteria that must be met in order for a question to be a valid scientific question. So these are the things I talked about regarding falsifiability, verifiability. Okay, and again, it's not enough to just know a word. Okay, you have to be able to explain these things. So you should know how to explain falsifiability, verifiability. All that means is that you have to be able to prove your hypothesis or whatever theory or scientific claim or whatever it is. You have to be able to either prove it true or prove it false with evidence. You have to be able to prove it true or prove it false with evidence, using evidence. Okay, so that's falsifiability. The next thing is reproducibility. Okay, so that means that your results have to be, other people need to be able to go and reproduce your results and obtain the same results. And it needs to be the sort of thing that you can do that, right? So like, for example, internal emotional experiences are not reproducible because nobody can go inside your brain and go inside your mind and experience those things, right? So that would be an example, one kind of far-fetched example of what wouldn't be reproducible, right? But also, generally speaking, even if you're doing something with experiments, those experiments need to be reproducible. Welcome. Do you need a study guide?
I don't.
Okay. And the last thing, it has to be based on observation, has to be empirical, and based on observations, furthermore, of the physical universe. Okay, so physical, external, objective universe. Okay, that's what we're interested in with science. Okay. So those are the 3 things. All right, what planets in our solar systems have oceans? You know that it's just the Earth, right? So I'm not going to spell everything here, but I'm just going to put a symbol. Okay, so we have, to date, we don't have really rock hard evidence of water on any other planets, at least not in our solar system. But there, however, in our solar system, there are some planetary bodies where we think there might be liquid water, perhaps even oceans, okay? Some of those are Europa, okay? And it's too hard to spell all these things from the mouse, but there's Europa and Enceladus, okay? Europa is a moon of Jupiter, Enceladus is a moon of Saturn, okay? And those are perhaps even Ganymede, which is another large moon of Jupiter. It's another option, okay? So yeah, there are some planetary bodies, satellites. You know, a satellite means something that goes, yeah, go ahead and grab it. So a satellite is something that rotates around a planet, right? So moons are satellites. So there are some satellites in our solar system that possibly have water. Okay, what are some features of Earth that were directly or indirectly created with water? And the main point here is almost everything, right? The atmosphere. The continents. I was trying to impress upon you last time that even the continents could not have been formed without water. You needed to form the continents. You needed to form the mountains, the erosive landscapes of our country or land. The atmosphere. Obviously all the lakes and rivers are obviously just water, right? So actually all the plant life, all the life requires water. Okay, so everything is about water and water on Earth, right? Almost it's incredibly formative to our planet. What percent of Earth's water is in the ocean? It's 97%. 97%. What percent of the Earth is covered with oceans? That's 71%. 5 oceans of the world. You would definitely want to know that. That's on there, right? So Atlantic, Pacific, Indian. There's also the southern, off the coast of Antarctica, and the Arctic there in the Arctic Circle. Okay. Which of those oceans is the largest? That's the Pacific. All right, now moving on to the metric system. Base metric system units for mass, length, and time. So mass is kilograms, length is meters, time is seconds. Okay. You should know also the prefixes, okay, the main prefixes that we talked about. So I'm going to write up here. You should know these prefixes. Sorry if you can't see this online, for my people viewing online. But we have our base unit, right? That's 10 to the 1, which is just 10. We can scale it up or down. We can scale it down with deci, that's 10 to the negative 1. Centa, that's 10 to the negative 2. Or milli, that's 10 to the negative 3, or 1/1000, okay? You can scale the base unit up and make it larger by tens with a deca. Sorry, that's 10 to the 0, which is 1. 10 to the 1, a hecta, 10 to the 2, or a kilo, 10 to the 3. You can scale it really large by doing a mega. Mega is 10 to the 6. Notice how there's a 3-point jump in between those. So these are different by an order of magnitude of 1,000. Okay. Notice how instead of going 1, 2, 3, we go 6. Do that. Okay. So mega is a million. Okay. 10 to the 6 is a million. We can also make it smaller by 10 to the 6 by doing a micro. It's 10 to the negative 6. Okay. So you should know those. You should know kind of how much they're scaling the base unit up or down, okay? So that's a million, 1,000, kilo 1,000, hecta 100, deca 10. Base unit is just the base unit 1. Deci, that's 1/10. Centa, 1/100th. Milli, 1/1000. And a micro is a 1/1,000,000th, okay? I don't ask beyond anything beyond that, okay? So I can't give a full lecture right now in metric system again, but hopefully that makes some sense to you. Those are the things you should know for the test. You need to be able to convert among all those, okay? So just to give you an example of how you would convert, let's do the most extreme. Let's say you have 1 megameter. I'm going to put a megameter. You have 1 megameter. How many micrometers in a megameter? So what you do is you've got a large unit, you're going to a smaller unit, so you move the decimal to the right, okay? And how many places do we have to move it? Now notice that we skipped, because you have to kind of use the exponents here, because it doesn't go just skipping by ones. See how it goes from 6 to 3 right there? So you have to use the exponents. What's the difference between 10 to the 6 and 10 to the negative 6? So 6 minus negative 6 is 12, right? So you would have to move the decimal point 12 spaces. Okay, so if you did that, you'd go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the most extreme thing you could ever have, right, on this test. Okay, and 10, so you would have, that'd be 1,000, that would be a million, a billion, a trillion, so you have a trillion. Okay. So there's a trillion micrometers in a megameter. That's what that's saying, okay? That's the most extreme you could ever have. Okay, probably what you're gonna have to do is jump like 3 places or something like that. Okay, like how many meters are in a kilometer, or how many centimeters are in a kilometer, or something like that. Okay. So I'm sorry if that doesn't make what went over your head, but you have to go fast. Okay. So how many millimeters are in 11 kilometers? How many millimeters are in 11 kilometers? Okay, there's 11 kilometers. There's the decimal point. To go from kilo to I'm saying millimeters. Is that what I said? Okay, kilo is 10 to the 3. Millimeters is 10 to the negative 3. The difference between 3 and negative 3 is 6, right? 3 minus negative 3 is 6. So I'm going to go 1, 2, 3, 4, 5, 6. You see that would be 11 million. Okay. Now for this one, how many kilometers are in 10 miles? the way I think, if I recall correctly, the way that this is asked on the test is in such a way that if you kind of know like ballpark, you'll be okay. I think. I don't want to promise you, but I think if you just kind of know ballpark. So like the way that this would probably be on the test. How many kilometers are in 10 miles? So there are 1.6 kilometers in a mile. So the correct answer would be 16 miles, okay? Now, probably this is going to be multiple choice, and it'll just be like this. How many kilometers are in 10 miles? 16, 160, 1,600, or something like that. Do you see what I mean? So if you kind of have some sense about conversion factors, I think you'll be okay with those kinds of questions going from English to metric system units. Okay, so I'm just going to keep it there because that's kind of a time-consuming question, so I don't want to do it right now. All right, lines that divide up Earth and extend from one pole to the other. Oh, by the way, does everybody know these different conversion factors? Centimeter to an inch, 2.54 centimeters per inch. Kilometer per mile, 1.6 kilometers per mile. Pounds per kg, there are 2.2 pounds per kg. 3.28 feet per meter. Okay, so if you have just some sense about these things, I think you'll be okay with those questions. Lines that divide up Earth and extend from one pole to the other are meridians. Okay, those are the lines of longitude. What's the special name given to that meridian? Do you all know that one? Prime meridian, right? Where do meridians intersect? Yes, they intersect at the poles. Okay. Do parallels intersect? No. Okay, they don't intersect. Which parallel is furthest from the poles? It's the equator, right? What's the climate like around just high latitude, right? 75. So by the way, anything over 66 degrees, between 66 and 90, that's going to be high latitude. So those are all Arctic, Antarctic polar conditions, okay? So it's cold. 75 degrees north or south is cold.
What was 16 again?
Meridians. Okay, what's the climate like around 10 degrees north? 10 degrees north is very close. That's in the tropics, right? Because anything between 23.5 north or south is the tropics, okay? So that's going to be hot, right? It's going to be hot and humid, whatever. Tropical. All right, for this one, you have to draw in. This is just like you had on the. I'm going to draw this in for you so you can see it, right? Wants you to draw in 45 north, 15 east, 10 south, okay? And label, and also the prime meridian. So I'm going to do this for you and show you how it goes, okay? So I'm going to sit down here. Now the prime meridian has to go through Greenwich, okay? But it also has to go through every pole. So a lot of people did this. Is that right? No, that's not right, okay? Because it doesn't go through the pole. So it has to be like a nice curving arc like that. Doesn't have to be perfect, but it does have to go through Greenwich and it has to go through each pole. So that's the prime meridian, okay? The next thing we're going to draw is 15 east. 15 east is going to be a little bit to the east of the prime, and it has to go through each pole. 45 north is going to be just about right here. Greenwich is about 55 north, so be a little bit under Greenwich. If you did this, I would give it to you. Okay, so but it has to be on the right, correct side of the hemisphere. It has to be on the north, and it has to be kind of somewhere close. Doesn't have to be perfect, but it has to be close-ish. Okay, and then the equator is already in there for you. So that's how you do that problem. Okay, now the one on the test, this is on the test. It's going to ask you for different lines than I gave you, and it's also going to be a little bit different than what you see here. So I'm going to put Greenwich somewhere a little bit different. Okay. All right, tilt to the rotational axis relative to the ecliptic plane. That's 23.5. Okay. Now over here, this is, so a lot of people get this one wrong. I can't remember if this is on the test or not, but it might be. But a lot of people get this one wrong. So this over here is the winter time, and you can see that the northern hemisphere is pointing away from the sun there, okay? And this one, you can see that the northern hemisphere is pointing towards the sun. That makes that the summer, okay? And that makes this one the winter. And then, of course, things always go counterclockwise. So between winter and summer, you have the springtime, right? So I'm going to put a V for vernal, the vernal equinox, and over here is the autumnal equinox. Okay. All right, which planets are? I already answered that. It's just Earth. Okay, number 26. A little bit about the Goldilocks zone. So the Goldilocks zone, remember, is the zone in a solar system. Doesn't necessarily have to be our solar system, but any solar system in which you could have liquid water. So you have to be the correct distance away from the sun to have liquid water. You also have to be the correct size, and you have to be, so I'm answering number 28 as well. It has to be the correct size to maintain stable plate tectonics that will actually release the water from the interior of the planet. Okay, has to be the correct distance from the sun to get the correct composition and also the right temperature range. And it has to be, a third thing that you could write for number 28 is it has to have a stable orbit. Because if your orbit is crazy, you can get temperature extremes that will make liquid water impossible to maintain on Earth.
The Goldilocks zone, is that in our solar system or it's just anywhere?
It's anywhere. It's anywhere. So it's just a term that refers to the correct distance from the sun in which you could have. It's just right for having liquid water oceans. Okay, we are obviously in the Goldilocks zone, but it's an area that is of great interest to scientists who are looking for liquid water on other planets, mostly so that they can find life on other planets if such life exists. All right, what percent of Earth's water is in the oceans? We already talked about that, 97%. How much water is stored in the mantle? We're not sure, but we think that up to 50% of all of Earth's actual water. See, I should actually be more careful. In number 29, I am careful. What percent of Earth's surface water is in the ocean? 97%. Is there water possibly still in the mantle? Yes, and we think possibly there's as much water on the surface as there is in the mantle. So we think there's a whole nother ocean in the mantle, if you want to call it an ocean. But it's stored in a mineral called ringwoodite that's in the deep mantle. So, all right. So moving on, who developed the Big Bang theory? That's Father Lemaitre. So it's a Belgian priest and scientist, Father Lemaitre. Georges Lemaitre. That was in 1927. What does the Big Bang theory state? Well, it states that all time, space, energy, matter began at a single moment, at what's called a singularity, and that the universe has been expanding in both time and space from that point. So time and space have been expanding from that point, we say. Okay, how long ago do we think the Big Bang occurred? That's 13.7 billion is the date. Okay, what element was most prevalent in the universe? That's hydrogen. Okay, and by the way, that's still true. Hydrogen is still the most abundant element in the universe. Okay, and it's been that way since the very beginning. Okay, given like 100 seconds after the universe was started. Okay, it's been true. What isotope of what element is synthesized by the hydrogen burning process? That's helium-4. So remember that 4 hydrogens fuse together but in a nuclear reaction, releases a lot of energy. That's the energy of the sun. That creates the isotope helium-4. Okay. What is the nuclear reaction that forms carbon in a star? That's what's called the triple alpha process. The triple alpha process. That's where 3 helium-4s fuse to give you carbon-12. Okay, and that's where all of our carbon comes from. Not all of it, but most of it. Okay, what is the source of all our solar energy? It's these processes. It's these nucleosynthesis, stellar nucleosynthesis processes, where there's fusion of hydrogen, fusion of helium, and other elements in the core of a star. So that's what's releasing all the energy and gives us all our lovely sunshine, right? So it's all hydrogen Mostly it's hydrogen fusion. All right, what planets in our solar system orbit within the ice line? That's the first 4 planets, the terrestrial planets, the rocky planets. So those are Earth, Mercury, I'm putting them in the bad order, Mercury, Venus, Earth, and Mars. Okay, those are the ice, within the ice line. Outside of the ice line, where it gets too cold to maintain kind of gaseous or liquid states. So everything is solid out there. So beyond the ice line, you have only solids. That's Jupiter, Saturn, Uranus, Neptune. Okay, how does the composition of planets within the ice line differ from planets outside the ice line? Planets within the ice line are small, rocky, and metallic. Small, rocky, and metallic. The ones outside are very large, very massive, and they are mostly gases, mostly hydrogen, some helium, ammonia, methane, carbon dioxide, lighter elements, relatively lighter elements. Elements with a smaller atomic number. All right, what's the ultimate source of Earth's internal heat? You know, it's hot down there in the mantle. Why is it so hot? It's hot because of the original, what's called primordial, thank you, primordial heat from the accretion of the Earth. Okay, and also from radioactive decay of various isotopes, especially potassium-40, the whole uranium series. In the old days used to be aluminum-26. Aluminum-26 is now depleted, but all those things are sources of heat for the interior of the Earth. All right, some different hypotheses. I remember this is on the test, so you want to know, you can actually just put 2 hypotheses here. Okay, the first, where did Earth's water come from? First idea is that it came from just the internal, maybe there was water in the minerals of the mantle, right, in the original accretionary material, the meteorites and asteroids, and it just developed from outgassing of the mantle. That's probably the most popular theory, but it's a very, very active topic. Actually, a lot of students who did the discussion posts talked about this, because it's an area of very intense and active research right now. Another source is possibly comets. Okay, that maybe we got hit with a comet early in our formation. Okay, which is nice because it explains why Earth has water and Venus and Mars do not. Okay, because that's kind of mysterious why, especially Venus, because Venus is so very similar to Earth, yet doesn't have water. All right, what was Earth's earliest atmosphere like? Okay, the most important point here, there was no oxygen. Remember that oxygen came from photosynthesis. You had to do some reading about the great oxygenation event, you know. Hey, welcome. So just remember there was no oxygen. It was probably a lot like Mars or Venus, where it's mostly carbon dioxide. Probably other things, probably hydrogen or methane, things like that as well. But it's probably mostly carbon dioxide. Okay. Okay, and which of the 4 basic layers of Earth do we get convection? Well, the main thing you want to remember here is definitely the mantle. Okay, definitely the mantle. And I'm sorry, Hayden, I ran out of study guides. But it's definitely the mantle. Okay, and then also you can mention the outer core as well. Okay, because there's convection in the outer core. That's what creates the magnetic field. All right, what are 4 differences between the continental and oceanic crusts? Okay, so there's a lot of things actually beyond 4 that you could mention here. Sorry, but you could mention first of all, there's a density difference. Okay, so what is denser? It's the ocean crust. Okay, continental crust is too light to subduct and get sucked back into the mantle. Okay, that's a very important difference. Okay, so there's a density difference. Ocean crust is denser. Ocean crust also is made of a different rock type. Ocean crust is made out of basalt. Okay, it's that black rock. On the other hand, continental crust is made out of stuff that's more like granite, more like, it's actually, correct name is diorite. It's not granite, true granite. It's a diorite. So there's a rock difference. Kind of rocks that make it up are different. You could also mention an elevation difference, right? The continental crust is, on average, a lot higher than the ocean crust. Ocean crust is got an average elevation of -4 kilometers, right? 4 kilometers below sea level. Continental crust has an average elevation about 500 meters above sea level. Okay. Another difference you could mention is thickness. Continental crust is thicker, about 30 kilometers on average. Ocean crust is thinner, about 5 kilometers on average, 5 to 7 kilometers. Okay. So all differences you could mention. And I don't know if that is on the test, but it is probably. I'd say more than a 50% chance it's on there. All right. You need to be able to draw a picture. Let me draw this for you so you see what this is supposed to look like. Because some people kind of draw this the wrong way, and this might be on the test, so just want to get out of that there. This thing, come on, there we go. Okay. So let me show you kind of what I'm expecting for this. If I ask this on the test, which I might, I can't remember. Okay, first you have the continental crust. Draw, there we go. Let's do the continental crust, okay? So you have the continental crust, it's rather thick, okay? Then it's going to taper out, and you're going to have the ocean crust, okay? And then below that, you have the mantle asthenosphere, mantle lithosphere boundary. So that's mantle lithosphere, this is mantle asthenosphere. Okay, this is ocean crust. This is continental crust. Okay, and then remember that the MOHO is just this boundary between crust and mantle. So this is the MOHO here. It's just the boundary between crust and mantle. Make sure that you don't draw two lines here, because I noticed that some people drew like another line. So like this is the MOHO, and then like that's not the MOHO. The MOHO is this line right here that you already drew. Okay, it's just the boundary between the crust and the mantle. Okay, all right. So that's how that is basically supposed to look. Do not draw this. So many people draw this. Like the core, you know, and what's the problem with that? Yeah, so if you do that, you're showing 6,400 kilometers of Earth. Okay, I'm just asking you top 100. So that's not right. so don't do that. Bad. Okay, scribble that all out. All right, MOHO is just the difference between it's the boundary between the crust and the mantle. Okay. I don't know what questions from your reading is here. That's not supposed to be there. I just copied and pasted that accidentally. Okay, so oh, these are from the reading actually, huh? Yeah, these are from the reading. So you're supposed to have done the reading, and hopefully you did. But what's isostatic adjustment in the context of Earth's crust and mantle? So that's isostasy. So it's just that the density of the different crust types, right? The continental crust and the ocean crust, they're going to reach a gravitational equilibrium with the mantle. Because remember, the mantle is solid, but it still is pliable. It's plastic. And so denser rocks, denser crust is going to sink deeper into that mantle. Lighter, more buoyant continental crust is going to be popped up and kind of floating a little bit more on that mantle asthenosphere. Okay, so that's kind of what I'm getting at there. The Great Oxygenation Event is the event that occurred about 2.5 billion years ago, in which you had a sudden increase in oxygen, free oxygen in the atmosphere, that arose from the evolution of photosynthetic life. Okay, so that's what that's about. Remember, all oxygen in the atmosphere is from photosynthesis. Okay, we didn't start off that way. It came later. Why do scientists think the Earth is 4.5 billion years? This is where you have to explain a little bit about radiometric dating. And all you simply have to say here is just know that, you know, there are radioactive isotopes in the world, and they decay at a very precise rate, a very certain rate. And based off that rate of decay and how much of the original parent isotope and how much there is the daughter isotope, we can figure out how much how much has decayed and how much time has passed. And that's the basic gist of radioactive decay and radiometric dating. Okay, so that's all you have to explain now. All right, so going into history of marine sciences, what are some of the ancient, as in BC time period, civilizations that were engaged in ocean exploration? These are the Minoans, the Phoenicians, the Egyptians, the Greeks. Okay, that's what I'm looking for there. And how were they primarily powered? How were those vessels powered in ancient times? You know, I got different answers for this, but the correct answer is with oars. Okay, so it wasn't so much sailing. You know, they haven't really developed the correct kind of rigging and sail types to do a lot of sailing. So most things, all the way up into the Renaissance, into the 1500s, was all oar driven. So manpower, right? That's what it was coming from. All right, what's the significance of Library of Alexandria? Remember that was a very important port city on the North African coast, the Carthaginian coast in the Mediterranean. They had a huge, the largest collection in antiquity of scrolls and documents, maps, charts, and it allowed people to, for the first time, put together a world map. Wow, what's a big deal? Okay, to have the first world map that showed a very good deal of the Eastern Hemisphere. Of course, the people there didn't know about the Western Hemisphere yet, right? So they didn't know about the Americas yet. So Ptolemy of Alexandria was the man who first put that map together, so that's why he's significant. And it's a pretty impressive map for being, you know, in BC times, right? It shows quite a bit of Africa, India, China, et cetera, et cetera. All right, so which Greek philosopher determined the circumference of the Earth, 270 BC, long time ago? That was Eratosthenes. I'll put. Can you all spell that phonetically? Do I need to spell it? Okay, I'll write it. Excuse me. It's something like that. I don't know if that's exactly how it's spelled, but it's something close to that. Erastus. I feel like I have too many syllables in there. Oh, it might be Aristophanes. Something like that. You don't have to get it exactly right. Aristophanes. It might just be Aristophanes. I can't remember. I have to look it up now. I'm curious. Yeah, there you go. Oh wait, no, Eratosthenes. Yeah. Oh, maybe I had it. Oh, there's no. There. That's what I erased the wrong T out. T up here. Eratosthenes. Okay. Anyway, sorry for that. Okay, after the fall of Rome, we had the European Dark Ages. Remember that China sort of took over in terms of making advances in marine sciences, right? So they're the ones that came up with, like, for example, the compass, the central rudder, which is a very important advance in shipbuilding. They came up with compartmentalized hulls, which is very important. So those are some of the technological advances made by China during the European Dark Ages. Now in 1453 AD, what happened there in Europe was, or I should say, actually kind of more the Middle East, was the fall of Constantinople. And that drastically altered political boundaries that effectively cut off trade in Europe from the Far East. So Europeans started trying to go to the oceans, to the seas, to discover new routes to make it to the Far East. So that's why that was a major import. It's because it drove marine science exploration during the Renaissance. Okay, who are some primary European ocean explorers, 15th to 16th century? You know, one everybody knows, Christopher Columbus, of course. You probably have heard of Magellan too, right? Ferdinand Magellan. You might have heard of Prince Henry the Navigator. So these were all very important figures who, discovered a lot, or I should say discovered for the Eastern Hemisphere, the Western Hemisphere, right? So before that, a lot of people had forgotten or did not know about the whole Western Hemisphere of the world. So who are some of the, what are some of Captain James Cook's major contributions to ocean exploration? So this was an 18th century British explorer, commissioned by the Royal Society of Britain, and he did a lot of explorations, discovered a lot of islands that had never, so Hawaii, for instance, Tahiti, a lot of the South Pacific islands he discovered for the Europeans. He also discovered, was the first person to sail within sight of Antarctica. So he sailed further south than anybody had ever sailed before. Okay, so those were some of his major contributions. Okay. So how could ocean navigators determine their latitude and longitude on the open ocean before GPS? So you just want to mention here, you don't have to go into great detail, but latitude they can get by the North Star. So the distance above, angular distance, above the horizon of the North Star gives you your latitude. Okay, so that's one easy way you can do it. Another way, so if you're going like this, you see the North Star like this, you're at a high latitude. If you see the North Star near the horizon, you're at a low latitude. Okay, so that's one way that you can determine your latitude. Another way, a way to determine your longitude is with a time-keeping device, like a watch or a clock that is very precise. And what you do is you keep track of what time the sun hits its meridian point, the time of noon, right? And as you know, with time zones, that changes based on your longitude, how far east or west you are, okay? So that's how they would keep track of their longitude, based on exactly, how many, what time the noonday sun is coming up. And that's why, by the way, you might know that, does anybody happen to know how you break up a degree, like a longitude degree, the subdivisions of longitude degrees? You actually break them up into minutes and seconds. And so the origin of that word comes from the fact that that's how it used to be kept. That's how we used to keep track of those things. Okay, so it's by time. All right, so what year was the HMS Challenger expedition? That was in 1872 to 1876. What are 4 things the Challenger crew studied on their very important voyage? I'm pretty sure I asked about Challenger. Okay, Challenger was just such a groundbreaking, important. I'm probably asked about it on this and on the final exam as well. So you want to know everything about the Challenger. So they measured depth with sounding, right? And how did they do sounding? It's just a weight on a rope. Okay, that's how they did sounding at that time. So they measured depth. They measured salinity, surface salinity, just like some of you have measured salinity. Okay, they measured the ocean temperature, surface temperatures. They also took dredgings. That means kind of like scraping the muck off the bottom of the ocean to see what came up. It's from 4,000 meters deep. They also looked at new kind of marine species. They discovered like 7,000 new species, right, on that expedition. So, boy, you can imagine all the work they had to do. So, it was, a four-year voyage. So there was a lot of scientific work to do on there. Anyway, that's the HMS Challenger. You should know a little bit about modern oceanographic research vessels. I talked about 2 in this class. I talked about the Japanese Chikyu, and also, which is spelled Chikyu, Chikyu. And I also talked about the American Okeanos. So that's Okeanos, Okeanos Explorer. Okay. So those are major research vessels, huge research vessels, like 80-foot research vessels that have oil rigs and all sorts of things, have research. They have what do you call them? The ROVs, the remotely operated vehicles and all that. So they're very sophisticated. Cost, like $1 billion. All right, some technologies for the modern era. That we use in the modern era to study the oceans. We use multi-beam echo sounding. ROVs, remotely operated vehicles. We use also ocean drilling, right? So drilling into the sediments and the rocks of the ocean floor. We use satellite altimetry to measure ocean depths. So those are 4 technologies you should be aware of. All right, getting on here to plate tectonics. Mantle, solid or liquid? It's absolutely a solid. And what powers convection in the mantle? So what's powering mantle convection is the fact that the base of the mantle is very hot. It's 5,000 degrees Celsius, and the top of the mantle is relatively cool. It's still hot. It's like 600 degrees Celsius, but it's relatively cool. So that's what's powering the convection. It's just like the heat lamp, the lava lamp, sorry. That's what's powering it. Okay, what's the name of the single large continent suggested by Wegener? That's Pangaea. Oh, I'm sorry, I totally skipped a bunch of things. It's silly me. Okay, difference between mantle asthenosphere, mantle lithosphere. Mantle lithosphere is hard, brittle, stony, right? It breaks like a rock. You hit the lithosphere with a rock, crumbles. The asthenosphere is weak, relatively weak, pliable, foldable, plasticine. It can mold, it can bend, it's more like silly putty. All right, so the 4 lines of evidence that Alfred Wegener gave for continental drift. Again, knowing just 4 words isn't going to be enough here. You got to kind of understand these a little bit. So the 4 lines of evidence are from fossils. It's where you found the same fossil of a very definite land-based creature on multiple continents. Okay. Glaciation. So we find that there are glaciers, the directional indicators that are left by glaciers, like striations and things like that, all match up if you put the continents back together. Another one is matching coastlines. That one's the most obvious. You put the coastlines back together, you can put all the continents back together like a jigsaw puzzle, and they mostly match up, especially South America and Africa, sorry. And then the last one is from a kind of matching geology on the different continents. So if you go to the different continents, you'll find that the geologic units and the kinds of mountain belts and all these different things are the same. Okay. All right. Continent suggested by Wegener, where everything was together, was Pangaea. 3 lines of geophysical evidence that arose after World War II that supported continental drift. That was echo sounding, magnetic anomalies, so research into magnetic anomalies. Hello. And the last thing is radiometric dating, age dating of the seafloor. Okay. Now, what drives seafloor spreading? Well, gosh, I tried to make a line and got all messed up. Seafloor spreading, continental drift, and all of plate tectonics, that's mantle convection. Okay, that's what's driving it all. And mantle convection, in turn, is being driven by the temperature differences, the geothermal gradient, the temperature difference between the bottom of the mantle and the top of the mantle. All right, where is new seafloor generated? Where is it destroyed? It is generated at, do you all know? Mid-ocean ridges, right? It's destroyed at subduction zones. Very important. I think that's probably on there. So it's generated at mid-ocean ridges, destroyed at subduction zones. Why don't we get too many earthquakes in, I don't know why this says Arkansas, it's because I used to teach in Arkansas. Maybe I should say Texas. Why don't we get too many in Texas or Arkansas? It's because we're far away from a plate tectonic boundary. Okay, so that's why. We're far away from a plate tectonic boundary. Okay, which of these are divergent, convergent, or transform? So a subduction zone is convergent. Okay, so it's convergent. A spreading ridge is divergent. The Mariana Trench, you only get trenches at subduction zones, which are convergent. The East Africa Rift is divergent. A lot of people really want to make this transform, because I just don't have one that goes to transform. So that's, a rift is a divergent boundary. Okay, so that goes to divergent. San Andreas Fault, oh, sorry, I didn't see that. San Andreas Fault is transform, so that goes to transform. Okay, we're almost done. So, and we're going to finish like right on time. So, how do volcanoes form at subduction zones? So, remember, at subduction zones, the basic idea you want to memorize here is that at a subduction zone, ocean crust is sinking into the mantle. That ocean crust is inundated with water, the water is released, it lowers the melting temperature of the mantle. The water lowers the melting temperature of the mantle, and that's what causes the mantle to melt. All right, now give at least one characteristics of an ocean-continent convergent plate boundary. Of course, there's a lot of things you could mention. Ocean-continent convergent plate boundaries are subduction zones. So you could mention trenches. You can mention arc volcanism. You could mention flux melting, which is the addition of water to the mantle to lower the melting temperature of the mantle to generate the volcanism. Okay, there's just a lot of things that you can mention. You can mention accretionary wedges, things like that. So I think, you know, in your lecture assignment, you had to actually draw out, you know, a subduction zone. So any of those features that you drew in the subduction zone, you could mention. Continent-continent convergence, on the other hand, that's where two continents are colliding together, coming together, converging. That creates very intense mountain building. Okay, so that's where you get like the Himalayan mountains. Okay, that's where India's crashing into the Eurasian continent, so that generates the mountain building there. And how fast do plates move? I guess that's probably on there. I'd say probably. That's anywhere between 1 and 10 centimeters per year. Okay, so we got through it all. It's 10:58. So I'm going to now turn off this thing.